Hello everyone. Welcome to Analog Electronic Circuits lecture number 9 extra part 1. So in today's topic we will be discussing about high frequency model of BJT in detail. So each and every component in a BJT model represents the physical phenomena or the characteristics of the transistor. So far we have discussed with the hybrid pi model of BJT, and now we will be discussing about its high frequency component. Fine. So let's start with stepwise formation of the model. So over here, we will model the transistor into common emitter configuration. So for simplicity, we are defining this norm. So we have over here the NPN BJT. It's base emitter. Emitter is common. And here we define the current IB in this direction. Current IC is from right to left. And the input over here is VBE, the voltage across base and emitter, and voltage across collector and emitter is VCE. So this is the convention we will be using. So base, collector and emitter are the transistor terminals. So we'll be representing in a common emitter form. So here we will represent base terminal, collector terminal, and emitter terminal. And then we will build up the model based on that. Okay. So let's proceed forward. So we'll directly talk about the modern BJT circuit structure, which is used in the integrated circuits, right? So this is how the structure is made. So basically all the contacts over here are taken from the top. So that's the feature of integrated circuit. When you manufacture a BJT in the integrated circuit technology, then all the contacts are taken from the top. So we have the base terminal, which is made up of N plus region. Then we have emitter made up of P region, P silicon, and collector, which is made up of N silicon. And finally, we have a substrate, right, which is a P silicon, P plus silicon substrate, which is there. And here, what we are saying over here is that there are some internal terminals that see B, E, and C, that is base, emitter, and collector are the external terminals, right? Internally, this silicon substrate also have some resistance. So we can call it this as idealized internal base collector and emitter terminals, which is B dash, E dash, and C dash. So each of them will represent have some resistance, finite resistance of that silicon material, right? N plus P or N silicon material, right? So that is represented in the form of RB, RE, and RC. So basically the difference between C and C bar is that we have a resistance RE, RC, and difference between E and E bar, which is capital E is the external terminal, and E bar, E dash is my, not bar, the E dash is my internal emitter terminal. Okay, so here it is differentiated by RE resistance. Similarly, B and B dash is represented by RB internal resistance, right? So this we have to represent in the form of this model. So here we have external terminals B, base, emitter, and collector. Internal terminals B dash, C dash, and E dash. So in between them, B and B dash, we have RB resistance. C dash and C we have RC, and E dash and E we have RE. RB is also called as RBB dash, and RB is actually the base spreading resistance. It's a resistor connected between the base terminal and the internal base, which is B dash. Now we have next RC. RC is a resistor connected between collector and internal collector, right, which is C dash. And RE is the resistance resistor connected between emitter and internal emitter, right? So yeah, they are very small. RB, RC, and RE. Small RB, small RC, and small RE are very small values, and they are typically in the range of 2 to 5 ohms. RC and RE, whereas RB is in the range of base spreading resistor is in the range of 5 to 100 ohms. Okay, the values are quite small. Okay, so the first change over here in the model is that we have internal resistance for the internal terminals also. So internal terminals are B dash, C dash, and E dash, and external terminal notation is B, capital B, E, and C, denoted, I mean, representing base, emitter, and collector. Okay, so this is the first part of it. Now, these values are very small: RB, RC, and RE. Let's go to the next one. Let's talk about the input resistance of the BJT. RPi, or in the H parameter model, it's called as HI. We know that when we plot the input characteristics, which is IB versus VBE, this is the input characteristics of BJT, NP and BJT, and it indicates that as we go on increasing the value of VBE, your current IB, which is the base current, will increase exponentially. So what do we do is we consider a small segment of this exponential and linearized segment, which is a straight line, and that we represent the y coordinate of it as delta IB and x coordinate of it as delta VBE. So the slope will be over here as the straight line approximation of this exponential curve. Its slope will be given by y2 minus y1 upon x2 minus x1. That is delta IB upon delta VBE. That is nothing but my slope. And R pi, the resistance R pi, which is the internal resistance of the BJT, is 1 upon slope. So R pi value will be delta VBE upon delta IB, about the Q point. So let's say that center of this line, straight line approximation, is my Q point. Fine. So yeah, that is how we calculate R pi. And normally it is R pi, which is the input resistance of the BJT. Its value is ranging from 1 kilo ohms to 3 kilo ohms, right? And where it is connected between the base and the emitter terminal. It's representing the input resistance of the BJT, right? So here it is in the above model, we have added R pi over here, which is marked in red color, right? And here R pi is highlighted. So this is the change which we have for representing the input resistance of the BJT, right? R pi. I guess you are already familiar with R pi in the earlier we have seen in the hybrid pi model, but that is the origin of it, R pi. So basically, if you try to see carefully, BJT is a non-linear device. So when we say hybrid pi model or a high frequency model, we are trying to linearize the non-linear BJT characteristics. Okay, so that is what we are doing. Okay, so this is about R pi. Next, we go to the output resistance of the BJT, which is called as RO, right? So we know that in the output characteristics of BJT, which is VCE versus IC, IC is in milliamperes, the collector current increases with VCE due to early effect, right? You must have studied this, but let us revise that, right? And here you see that normally over here, once it crosses a certain voltage, VC value, right? VC saturation value, the current should remain constant, but it does not remain constant. It keeps on increasing slightly, right? So again, we can consider a straight line segment and we can determine the y coordinate as delta IC and x coordinate as delta VCE. So the straight line approximation here will be slope will be equal to delta IC upon delta VCE, right? And this is represented in the form of RO, and RO will be let us go down and check it out. RO will be 1 upon slope, which will be delta VCE upon delta IC. And RO value is normally very high, which is around 40 to 80 kilo ohms. Now let us briefly see what does the early effect says. So the effect of having this output resistance, how do we characterize this in the model? So we characterize this in the form of a resistance RO connected between C dash and E dash. Okay, connected between the internal terminals C dash and E dash, right? So that is what is highlighted over here. Now let's understand what is this early effect. So let me show you the cross-sectional view of a BJT. So this is an NPN BJT. This is my collector emitter. Basically here we have done something opposite. So this is my emitter. Okay, yeah, this is the in this case we have considered this as emitter, this as collector, and this as base. Okay, so area wise collector should be the largest one, but okay, we have done that slight error over here, but we can always consider that safely. So this is my collector terminal, base terminal, and emitter terminal. We know that the J1 is the base to collector junction, right? And over here, VBE is normally VBE of a BJT is forward bias, base emitter junction is forward bias, and base collector junction is reverse bias normally, right? So let's consider this. So what happens is, let's consider WBC as the width of this depletion layer. We know that there is a PN junction formed over here, right? And base collector junction is always reverse bias. And in reverse bias, the depletion width is very larger. So as you go on increasing your reverse bias potential, what will happen is, as you go on increasing your collector to emitter voltage, your base collector region will become more and more reverse bias. Correct? Because we are applying a positive value to the N silicon over here. Collector is N silicon. So it will become more and more reverse bias, base collector junction, because VB is kept constant almost in the output characteristics. So what really happens is, as your collector to emitter voltage increases, the width of the depletion region VBC increases. Therefore, the width of the effective width of the base region. So base region normally is this, right? From year to year. But due to the depletion region extending towards the base, the width, effective width of the base region reduces, right? So therefore, what will happen is, this will decrease the electron hole recombination in the base region, which is happening due to the diffusion process. So therefore, the number of electrons drifting to the collector will increase, and that will increase the IC, collector IC. This will increase the collector current IC. So again, I repeat, what happens is, as you go on increasing the value of VCE, the width of the depletion region WBC of the junction, base collector junction, will increase, and the effective width of the base will reduce. So there will be less number of electron hole recombination in the base region. So whatever electrons are coming from the emitter are drifted to the collector region. Okay. So the number of electrons drifting towards the collector increases, and that will increase the collector current IC. So this means that as your voltage across collector to emitter increases, your collector current increases, and that is what is called as early effect. And the result of early effect is that increase in the current IC due to increase in VCE instead of remaining constant. So yeah, the text is written over here. You can have a look at it. Okay. Remember, the collector region has the largest area. So here somehow I will correct it, and I will update this, and I will give it to you. The base region is the very thin, right, and very smallest area it has, and the collector is the largest, right. So that correction I will make. Else, other than that, the effect of the early effect is represented in the form of RO, right? Its significance is captured in the form of RO. So there is a slope in the characteristics. That slope is captured and converted into the output that represents the output resistance of the BJT in matter of speaking. So here it is represented RO in the high frequency model of the MOSFET. Fine with it? Okay, fine. And the RO value is typically 40 to 80 kilo ohms range. Now we move on to the next one. So for next one, we will go to the fourth point. Let me just go over here. Yeah. So next is, your BJT is a current control device. So your output current, that is collector current IC, is controlled by the input current IB. And the relation is very, very clear. IC is beta times IB. And beta is also called as HFE in the H parameter model. So this characteristics of transistor is shown in the model by a dependent current source. Normally your beta and HFE value is ranging from 40 to 300. So let me show how it is captured over here. Yeah, it is captured in the form of GM into V pi, right? It is captured in the form of GM into V pi. So your collector current will be given by beta times IB, correct? And your GM, your transconductance, is also given by the formula of IC upon VBE. Okay, collector current upon VBE, and your VBE is nothing but V pi, correct? So GM is basically IC upon VBE, correct? And VBE, if I want to represent it in the form of a current source IC, that will be GM into V pi, whereas V pi is nothing but VBE only, correct? So this phenomena is captured in the form of a voltage dependent current source GM into V pi. We have already seen this before. Fine. Now let's move on to the next one. So this is the addition. So whatever is the recent addition, it is marked in red color and it is highlighted. So GM into V pi is the current source. So that shows that BJT is a current control device. The amount of output current is controlled by the input current IB. Now, next is that collector base junction in a BJT is reverse bias. So there will exist a large resistance between the collector terminal and the base, right? And that is represented in the form of R mu, right? And let us check it out over here. Yeah. So here we have written over here R mu, and here normally your base and collector is open circuit because it is reverse bias. Base collector junction is reverse bias. Very less current flows through it, but eventually some leakage current flows, and that is represented in the form of R mu. And R mu value is basically around 5 to 50 mega ohms. Sorry, it's a mistake over here. It's R mu is 5 to 50 mega ohms. Let me correct that. Okay, here it's a PDF, so I will correct that document and I will update it. Okay, let me go back over here. Yeah, our mu value is 5 to 50 mega ohms. It's a very large value because it's reverse bias base collector junction. So R mu is connected between base B dash and C dash, right? Now let's move on to the next point. So next point is about the transition capacitance. So let me go back to the circuit now over here, right? Okay, so let's consider this now. This is my emitter, this is collector region, and this is my base region. It is a NP and BJT. And over here we have a junction, which is your base to collector junction, which is denoted by JBC. So this is the depletion region marked by the dotted line, red color dotted line over here. So what really happens is base collector junction in a BJT is reverse bias. So this will cause the depletion region to exist across the base collector junction. So depletion region doesn't have any free electron in it, correct? So let me redraw this base collector junction one more time. So at the base side we have P. Base is made up of P-type silicon, and collector is made up of N-type silicon, right? And in between that we have a this thing, depletion region. So depletion region doesn't have any free electron in it. Therefore, depletion region behaves like an insulator and works as a dielectric. Okay, works as a dielectric, while the P region and the N region will act as the plates with the positive and the negative charges. Correct. So since your P region will contain maximum holes, majority carrier holes, and collector region will have majority carrier electrons, so it will act as the two plates of a capacitor, right? Separated by a dielectric in the form of a depletion region. So basically, this is representation in the form of a capacitance. So this is represented as capacitance denoted by C mu. Okay, denoted by C mu, or it is also denoted by CBC, capital CBC. Here it is. Okay, this representation of capacitance is represented by C mu, CBC, or CT, and this is known as transition capacitance. Okay, I repeat, CBC, C mu, and CT, any one of that. And why it is so? Because when we change the voltage across the base and collector, that is a reverse bias, right? So what will happen is the depletion region width will increase and decrease, and that will eventually change the charges. So we know that the capacitor formula is dq by dv. So if there is a change in the voltage, there will be change in the charge, and that will represent the capacitance, right? So that's how we have in a reverse bias PN junction, we have a capacitance, right? And that capacitance is between base and collector. Normally it is over here internal base, that is B dash, and internal collector, which is C dash. So we are representing it in the form of a capacitance C mu. Is this clear to you all? Yeah. Why this capacitance exists? It is clear because of the reverse bias base collector junction. Okay, and this depletion region will keep on changing as the voltages will keep on changing externally applied to these terminals. Okay, so this is how we add over here C mu. Now let's go to the next part. Now next part is about another capacitance which is present in the NP and BJT. So we know the working of the N channel, I mean NP and BJT, right? I'm not discussing in the detail. So what really happens is whenever the base emitter junction is forward bias and base collector is reverse bias, so the electrons diffuse through the base emitter junction. Okay, the electron will diffuse because in BJT the current flow is due to diffusion phenomena. Diffusion is due to the concentration gradient. Whenever electrons, which are majority carriers, goes into the p region, they become minority carriers over there, right? So that this process is called as diffusion. So electrons diffuse through the base emitter region. Similarly, as base collector is reverse bias, the holes which are there in the p region, or the electrons which are coming over here, the holes which are there, holes will diffuse again through the base emitter region. Okay, fine. So what will happen is, due to this, there will be a charge storage in NP and BJT. And this is the picture over here, shown over here. We have emitter, base, and collector. In between, this region is called as base emitter depletion region, and this is base collector depletion region. So what happens is, as the electrons diffuse from emitter to base, or the holes will diffuse from base to the emitter, there will be minority charges which are getting accumulated near the base emitter depletion region, right? And why they get accumulated, we will see now shortly, right? So this is in the form of the cross sectional view. In near the base emitter junction, there is accumulation of holes onto the base side, and there is, I mean, onto the emitter side, and there is accumulation of electrons onto the base side of the junction, base emitter junction, forward bias base emitter junction, right? So why there is charge storage happening over here, we'll discuss now. So at low frequencies, the time available for the charge carriers to diffuse across the forward bias PN junction is more. Okay, so the carriers have sufficient time to diffuse across the across the base emitter junction. But this reality at higher frequency is different, because at higher frequency, the time required for the minority carriers to diffuse across the forward bias base emitter junction is quite small. Therefore, any electron coming from the emitter do not get enough time to diffuse through the uh, you know diffuse through the base emitter junction. Similarly, holes which are coming from the collector did not get enough time to diffuse through the forward bias base emitter junction. So this will cause accumulation of minority carriers, that is minority carrier holes, get accumulated on the emitter side of base emitter junction, and minority carrier electrons. Why minority carrier? Because in the base, it's a p-type material, and there is accumulation of minority carrier electrons over there. So minority carrier electrons will get accumulated at the base side of the base emitter junction. Okay. So this phenomena of minority carrier charge storage around the forward bias base emitter junction is represented in the model by a capacitor. Okay, so here you see there is a storage of charges. So this again you can consider it as a, base emitter junction is a dielectric, because depletion region, right? It's void of any carriers. And on the either side of the junction there are charge carriers. Here there are positive charge carriers, minority charge carriers, and here there are negative charge carriers. Electrons are negative charge carriers, right? So we have a positive plate, we have a negative plate separated by a dielectric. So again, it represents the capacitance, because as we increase the value of base emitter voltage, more and more of this, you know, diffusion will take place. But only problem is, at a very high frequency, this charge storage phenomena will be dominant. Okay, so therefore, only at higher frequencies such a phenomena exists, right? And that will contribute to, you can read the theory about it, that will contribute to something called as diffusion capacitance. Remember, this capacitance is happening in the forward bias base emitter junction. Okay, and that is represented as C pi, CD, and CBE. C pi or CD, capital CD, or CBE, and this is called as diffusion capacitance, right? And the C pi value is around 100 picofarad. So this phenomena is represented in the model with a capacitor connected between the base terminal and the emitter terminal in the form of C pi. It is highlighted in the red color, and C pi value is also highlighted. Okay, so this is due to the diffusion of carriers and the subsequent charge storage of minority carriers on the either side of base emitter junction, right? And that is what is representing, and that is applicable only at a higher frequencies. At low frequency, that charge storage problem is not there. The minority carriers diffuse easily, right? And they have enough time to cross the junction and go on to the other side. But at higher frequency, they don't have that much of the time, right, available. So that time is called as transit time, the time required for the carriers to diffuse across the junction, right? So that is a problem at higher frequency. Therefore, there is the existence of such a capacitor, which is C pi. Fine, clear about this? Now there is next phenomena which is coming up. Okay, so the eighth one. So in case of modern BJT structures, have an additional capacitance connected between collector and the substrate, which is denoted by CCS. As you can see over here, there is a substrate in integrated structure of a BJT. This is NPN, and we have a P silicon substrate. Correct. So this P plus substrate and N region over here is also reverse bias, because normally P silicon substrate is connected to the ground, right? And collector terminal is normally for a NPN transistor is connected to the positive side. So we have connected positive to the N region, and this P plus is connected to the ground. So P plus N region will be reverse bias. So if it is reverse bias, there will exist a capacitance over here, which is denoted by CCS, which is due to the reverse bias P plus N junction between the collector and the substrate. Okay, so it is called as C, denoted by CCS, and it is connected between the collector and the you know ground. Why? Because normally the substrate terminal over here is connected to the ground. Fine. So that is why in an integrated circuit, the substrate is normally connected to the ground. That is why this capacitor exists between the collector terminal, the internal collector terminal C dash, and ground, denoted by CCS. Yeah. So this capacitor exists because of the structure of the BJT, modern structure of the BJT, right? So now we'll see the complete high frequency model of the NPN BJT. So first we started with having the internal terminals B dash, C dash, and E dash. And we have seen that there is a resistance over there between the internal terminal and the external terminal, denoted by RB, RE, and RC. Then next we have considered the input resistance of a BJT is denoted by R pi, and the early effect is denoted by output resistance, which is RO. Then the current control part of the BJT is denoted by GM into V pi. Then between the base and collector, we have a very large resistance because of the reverse bias between the base and the collector, denoted by R mu. Then at higher frequency, the base emitter junction, the base collector junction is reverse bias, and it happens that there is a transition capacitance in the form of C mu. In the forward bias base emitter junction, right, we have just now seen that there is a transition capacitance in the form of C pi. And finally, we have CCS, which is the capacitance collected between the collector and the substrate. So this is the complete high frequency model of a NPN BJT, exact model of NPN BJT. Fine. But we will be using an approximate high frequency model for a bipolar junction transistor. So basically what happens is, in the complete high frequency model, let's look at this. In the complete high frequency model, RB, small RE, and small RC values can be taken as short. This can be considered as a short circuit because of their very small value. And in the high frequency model, okay, in the approximate high frequency model, and also R mu can be considered as open circuit. So remember, RB, RE, and RC are denoted by short circuit because of their value is very, very small. It's around 5 to 10 ohms. And R mu value is very, very large, 5 to 50 mega ohms. So R pi value can be replaced by open circuit, and RB, RE, and RC can be replaced by a short circuit. Okay. So that means there is no difference between the internal terminals B dash and B. We can directly write it as same only. So that's what we write over here. B dash is equal to B, C dash is equal to C, and E dash is equal to E. When can we write it? When we consider this approximation. That is small RE, small RB, and small RC can be taken as short due to the very small value, and R mu can be taken as open due to the large value. Okay. So what do? We ignore RB, RE, and R mu and RC for the high frequency analysis. So we are left out with this much. So this is my high frequency model. So the ones which is marked in black color is my hybrid pi model, which we have already seen. And the addition over here is the resistance which are marked in red in color, which is R pi connected between the base and emitter, R mu connected between the base and collector, and CCS, which is connected between the collector and the substrate, right? if you want to visualize it in the model in the modern BJT structure, which is used in the integrated circuits, it can be represented in this form. So between the emitter, which is made up of N plus region, and base, we have C pi, right? We have forward bias base emitter junction. Then between the collector and the base, we have C mu, which is a reverse bias PN junction. And between the collector and the substrate, we have CCS, okay, which is again reverse bias. So that is represented in this approximate high frequency model. So from now on, we will be using this approximate high frequency model of a BJT for an analysis. Fine. If you have any questions, you can ask. So for all the numericals and analysis, we will be following this approximate high frequency model from now on. Okay, with the addition of the three capacitors which is seen, which are active only at the higher frequency. So in the next extra lecture for AEC lecture number 9, we will be discussing about why these capacitors will only get activated at higher frequency, and why they are present only at the high frequency model. Okay, so that is all for this session. We have covered the entire journey and the origin of all the capacitors. We have also seen the exact model for a BJT, and finally we have seen the approximated model which we'll be using for an analysis. So this completes the topic of high frequency model of a BJT. So that's it for today. Thank you for joining.